So today we're very happy to have Eva Silverstein to give us the fourth quantum cosmology seminar on Timelike-bounded DS4, microstates and phenomenology. So thank you, Eva, and please take it away.
Great. Well, thanks to you, Stefano, and everybody who's organizing this. I think it's a great idea, and I've very much enjoyed the previous talks and discussions. Um, so this one is going to focus on sort of the most recent two papers in this series with wonderful collaborators Gonzalo, Gauri, Bruno, Sungyan, Evan, Vasu, Ronak, um, Aitor, and Angaran. So, although the latter will just be sort of a future direction. That's going to be the formal side of it, but with a little bit of a taste of a phenomenology project that's in the works with Oliver, Colin, and Gonzalo, with great input from others who've been enjoying discussing. We've all been enjoying discussing the question there. So, okay, let me. So that was, I already almost took the hour, mentioning all the collaborators. And if I tried to mention everybody who's been making interesting contributions to this subject, it would go on and on. This is a partial list. There's many more. And one of the nice things happening these days is there's synergy between different developments that a priori may have looked
Sorry,
rather.
Eva, I think we cannot see your screen if you're intending. At least I cannot see your screen. Can everyone else?
I can see it. Yeah,
I see
look,
it
look
fine.
on a separate window.
Ah,
Wait, why is it? So,
okay, don't worry. I'll figure it out.
well,
Hmm.
we can wait. I mean,
Okay, I found it. Yeah, thank you.
okay. Yeah, so all these people, many more, I'm sure. So one of the themes of this is going to be to take seriously the possibility, which is generic in terms of the topologies we might have in the universe, that there's a time-like boundary. Um, so then the bottom-up GR action has both the bulk and boundary terms. The form of the boundary term and the coefficient depends on what exactly you hold fixed. So sort of the most, the dumbest thing you might think about, which we will indeed use in a regime where it works, for a case that it works, is Dirichlet, where you hold fixed the proper geometry, the intrinsic geometry of the boundary. But of course, you can play with that and fix other combinations of the intrinsic geometry and the extrinsic curvature. So you can do something more like Neumann. You can do a mix of fixing parts of one or the other. That's the conformal boundary. An example is a conformal boundary condition. There's one called umbilic, where as tensors, the induced metric on the boundary is proportional to the extrinsic curvature, which has been nonlinearly shown to be a good solution to the collection of consistency conditions that we have in this setting, which is known as the initial boundary value problem. So this goes beyond just having a good variational principle, which is just the sort of 0th step. And as I'll say a little more about, there are cases of Dirichlet that are fine. When people say Dirichlet doesn't work, they mean if you insist on being able to fix any choice of boundary geometry, then you can easily see, and I'll show it on the next slide, that you can't be that greedy. However, you can fix the kind of intrinsic geometry of the boundary that we're going to be interested in here. And as I already mentioned, there's other examples. People are still working out the details of this conformal boundary condition. And there's a wonderful set of works on this subject, both in GR and lately people have started attacking the problem in perturbative string theory as well. So I'll just say a little bit about the issues that come up in this. So just focusing on the case of Dirichlet, just to be concrete, and it's because what we'll use. The issues that can come up include, existence of solutions is not guaranteed. Now, this is something that's very, very intuitive, very familiar, really. So if you think about the sort of radial evolution analog of the constraints of GR, those are powerful, and they don't let you do whatever you want on the slice on which you define those sort of radial initial conditions if you want. So For example, if you insist on having a homogeneous, negatively curved, radial initial data, too bad, you can't solve the radial analog of the constraint. And so this isn't very subtle. You can easily see that you can't have any choice you want for the boundary intrinsic geometry. Another issue that's interesting in the Lorentzian signature setting that we'll be in the whole time today is geometric uniqueness. So, you're trying to set your initial data on some time slice which exist in your bounded universe. So you want to pose the initial data within the bounded region, but a cartoon, which is pretty accurate of what can go wrong, is that you could have some mode that you could formulate as if it lived outside your bounded region, where if you didn't have the boundary at all, this mode would just be pure gauge. However, it can formally propagate to the boundary, at which point it can become physical. And if you think about that, that's a way in which you see that you can fail to have geometric uniqueness. So you can put your initial data here on this slice and evolve forward, but suddenly some, ghost, not ghost literally, but some, excitation happens that really originated from this, in some formulation from this pure gauge mode outside. So that would tell you, what that the initial data you put was not enough to tell you what happens later. So that's the kind of thing that can go wrong. Now, one of the interesting developments, this is a live subject in GR, and some of our friends on this call have done important work on it recently. So one thing to be aware of is that this example that I gave was worked out most traditionally in the case of a flat boundary in Minkowski space. And you might think, oh, okay, for any boundary, I could take, arbitrarily short scale momenta and I'll get into the same problem. But of course, let's not do that because that would go way out of the regime of validity of GR. If instead you keep, say, you think now about a case where the boundary isn't flat, but it's a sphere, and you keep the angular momenta, you look at them one by one. So you have some equations for modes like this. I'm just kind of lazily copy pasting from this paper by Aninos, Chaucorn, and Gallant, where they show that the equation, the moment you think about a sphere, boundary, intrinsic geometry, or a cylinder if you include the time direction, well, then these equations that led to this geometric non-uniqueness, those become incompatible with each other. Okay, so that is interesting because it says that this particular pathology of Dirichlet in the general case goes away in this case at the linearized level. Now, there's a group of mathematicians, Michael Anderson and on, same people who have been developing this conformal boundary condition, but they're also looking at Dirichlet and generalizing this to a nonlinear statement. Sorry, I have what I was authorized to share about that somewhere below, but basically they do a nonlinear proof of the validity of this, which is nonlinear valid at short times in the sense that then later black holes can form and so on. But this is just to say that the statement that Dirichlet is viable is getting coming out from these kinds of analyses people are doing. Okay. Okay, so coming back to super big picture, we want to understand the positive CC. The cosmic horizon has implications for the origin of structure, thanks to the classic and ongoing works on inflation. And the cosmic horizon also has this really tantalizing suggestion of a much more microscopic entropy associated with it, a finite but ginormous number, the Gibbons-Hawking value. And so, this kind of very briefly summarizes the two sides of the subject, which we all are pushing on. And this talk will mostly sort of be on the formal side, but I will also share a phenomenological outgrowth of some of this work as well. So as I say, in this talk, we're going to take seriously the possibility that we have a more generic topology of the universe than just a closed universe, and in particular have one or more time-like boundaries. The virtue of this from the point of view of the formal side of the subject is that that will immediately make sense of a non-trivial energy spectrum. So because of the boundary, the energy is no longer constrained to zero. And that opens up the possibility to look for a count of states interpretation of the given talking entropy. And on the pheno side, I realized, although people have done interesting checks for certain kinds of topology in the universe, they haven't happened to do this one, and so it's a fun exercise to carry that out, which is still work in progress. Okay, so I already said this. Basically, if you have this set up with a fixed boundary geometry, the energy is not constrained to zero. In that respect, it's like ADS-CFT. There's a spectrum of energies. And the main result I'm going to share, which by no means answers all questions we might like to answer about de Sitter and cosmology, but answers some questions, is to construct a prescription for a finite quantum Hamiltonian system, recently generalized from a three-dimensional version of this to a four-dimensional one. And the goal will be to do that in a way such that the spectrum produces of this Hamiltonian system, produces a cosmic horizon microstate count while also reproducing the geometry of a patch of de Sitter. So I want to stress that what this will capture is as drawn in this cartoon figure, which is a set of states with some band of energy levels that corresponds to the cosmic horizon patch, which is to say just the usual observer patch, but with a time-like boundary there. There are other states that get quite messy, but sort of at the bottom of the spectrum, you have what we call the pole patch, as opposed to the top, which was this cosmic horizon patch. The pole patch is the one where you have the same time-like boundary, but fill in the other way. These are all energy levels or bands of energy levels in the system. And I want to note that we have shaded the patches that I just said in words, and we do not have a statement about, one can work on that. I'll get to that in the future directions part, but we don't have a statement going beyond that to the future of the decaying de Sitter and all that, which is a great goal too. But the point of this talk is to propose an answer to instead the question of whether there's a microstate count, which matches the de Sitter entropy and the geometry, not of necessarily the whole system, the whole extended de Sitter geometry, but at least these patches. Okay, so that's the plan. Before I get into details, I'm just going to sort of summarize. It's going to be a pretty elaborate procedure to construct this theory, which involves sort of four types of deformations of the Hamiltonian. We'll start with a Hamiltonian of an ADS-CFT system, and we'll do a bunch of deformations of that. Just to anticipate a little bit, this thing will have sort of two main components. One of them is a solvable deformation, one in which we can we'll deform the Hamiltonian in a way that generalizes the TT bar deformation in any dimension. But let's focus on four dimensions, which by itself is solvable. We can say we're adding a certain operator and then solve for the effect of that on the energy spectrum. And this by itself doesn't capture everything, but it captures the state count of de Sitter, and at the same time it captures the radial geometry. So this T is going to be related to the notion of energy that we have, which many of you will know is the Brown-York energy. The value that takes is a function of how big the boundary is. So that's what I mean by radial geometry. There's a geometric prediction for how the energy, the GR notion of energy, changes as you change the size of the boundary. So the solvable deformation, if that's all we did, would capture these things and not capture other things. But what's nice about it is that it's capturing kind of the most entropic stuff in the system to very good approximation. However, in the end of the day, we won't just do that. We'll do that as a very high energy cutoff on the system. But then after that, we'll include a second component to this, which is a massively fine-tuned what we call algorithm to include the parts of the deformation we need that will match to less entropic but important details of the bulk. So the bulk includes gravitons flying around, matter fields flying around, even domain walls, because we're talking about the ADS and DS and flat 0 CC landscape. And so there's a messy set of stuff that we'll need to tune our heads off to capture. And the point of that is basically that we can do that with the same state count, same huge but finite Hamiltonian system, and that therefore doesn't ruin the result of the nice part of it, the first solvable part of it. Okay, so that's the point. Okay, so there's going to be a couple of assumptions, as I said in my abstract, that goes into this. One is that the Dirichlet boundary condition does make sense. There's evidence for that that's serious that I already listed. Another thing we noticed is that if there's this classical problem, there's also the quantum problem. That's the one we care about at the end of the day. This business of non-uniqueness, if you think about it, requires degeneracy. It requires there to be multiple states with the same energy in a setting like we have, let's say, where we have time translation symmetry. So actually, with a quantum system that in the sort of classical coarse grain description looks right for gravity, it's pretty easy to remove the degeneracy. So anyway, I think there's good evidence for this, but it's definitely a thing to continue to push on from all sides, including not just GR, but also string theory. And of course, like I said, there's other types of boundary conditions one can play with. I'm also going to get into what we need about the landscape. And there's an assumption here, which is that the landscape is connected. This is something we've seen over and over again in developing string theory. And we've seen some analog of what we need, where some extended object condenses and changes topology. We don't know, nobody has worked this out in the particular uplift of ADS times ADS 4 times S7 to hyperbolic compactification that we care about here. So I'll list this as an assumption. I think it's plausible, but certainly it would take a lot more to actually prove it. Okay, so there's a lot of interesting progress going on involving a kind of time-like feature, and they have some overlaps, but so let me comment on the relation to the notion of an observer, which already makes a better sense of entropy. In one way, people have talked about this is this business of algebras, where it gets you to type 2 starting from a kind of field theory, bulk field theory analysis, taking G Newton to 0. We're going to be in type 1 land, which is, I always joke, is type 1 fun, just like with mountain climbing. And these have some overlap in making sense of entropy, and in some ways making sense of energy. Though in my view, part of the reason I'm taking this time-like boundary thing seriously as at least something to develop is that it does so, I think, more sharply because it just has an energy spectrum. It's not shared with another entity in the same closed universe system. So in that sense, it's actually, to me, a bit easier to think about, a bit cleaner. But they are related ideas. In fact, you can view a time-like boundary as kind of an intermediate step in calculations involving the observer. And that's come out in recent papers that we've seen in the literature that I'll refer to later. But when a push comes to shove and you just ask, are these the same thing? They're not. So a time-like boundary just as it is, not then sewed to a bigger space-time, that is a different topology of the universe. It's not the same thing as some massive particle, with or without a conscious entropy of its own. And the dynamics and the phenomenology are different. Okay, so let me go to the phenomenology interlude I promised, which is, okay, so I've already stressed this thing that we don't know what the topology of the universe is. I doubt we'll ever know, but we will do our due diligence to try to do the optimal search for these time-like boundaries in the universe. In terms of the physics of it, the dynamics of it, they're different. One way to see that is like if we have this time-like boundary that I've sketched here, it's surrounding a time-like trajectory. However, there's this good solution to the initial boundary value problem for it. There's this, in particular, there exist solutions where it doesn't warp the ambient de Sitter solution at all. It just doesn't do that. So in one respect, that it's like on this time-like trajectory, it's kind of as if it were a massive particle. But in another respect, it's definitely not like a massive particle because it's not sourcing any back reaction on the space-time. Okay, so because of that, we need to do, and we're starting to have fun doing try to develop an optimal search strategy in real data. Now, once you start doing something like this, you're confronted with the problem of there being many, many ways this could work, and many parameters in sort of the theory space of this a priori. I think we're going to be able to distill it down to some characteristics effects, but I won't say too much, just a couple of immediate effects that we could work out so far without yet doing the tests and data. I think I mentioned, it's not like this is a new idea to test for topology in the universe. There are papers by various cosmological luminaries doing this in the past for other types of topology. Somehow no one did this type, and we've been talking with these guys about it to some extent. Here's a nice illustration of a kind of effect that these can have. This is a simulation, a quick simulation due to Oliver. So imagine that we have a boundary and we're here, and the boundary is kind of close, or it's obstructing, but close by to what used to be the usual last scattering surface in cosmology. So where the CMB photons emanate from. Well, you can see quite easily and intuitively what's going to happen to that. So this boundary, being like a mirror for these photons, will obstruct what was behind it. But what you will see is CMB photons that hit you, the observer here in the middle, after having bounced off the boundary. And so there's this sort of bigger blue partial circle locus that is where those photons come from. And so you can see that they're going to look to you like they're still in this angular window that is obstructed by the boundary. So within that angular window, there's going to be a lot of modes that are just concentrated there. And so that's why in the two pictures, the left is like the fiducial CMB and the right is the thing with this boundary. You see that that has happened, that there's a lot of short scale physics, short scale modes within this angular opening angle. Okay, and just as a sanity check, these things could be enormous and we wouldn't really see them because, well, the CMB is prodigious. Its resolution is, of course, finite, and way out here it can be 10 megaparsecs. You can scale that back and still, have pretty enormous features that, at least at this quick level of an estimate, we would be none the wiser. Okay, so another thing that they do though is they infect the primordial perturbations in the first place. So depending on the scenario, one can compute that Green's function, that 2-point functions. There's kind of a mirror image type analysis of it. It's helpful that the modes, as we go back in time, they become shorter and shorter, so they can easily be frees out shorter than the wall, and it can look pretty flat, and you can thereby have a relatively easy time estimating the 2-point function. So in general, there could be these two effects happening that need to be combined. Of course, there could be more boundaries, there could be all sorts of other stuff. Another thing I should say, which is a sort of limiting factor to the motivation, is that just like with monopoles and so on, these things could easily have been diluted too far away. But we'll do our best. Okay, so now let me come back to the sort of formalities. We all know there's some thermodynamic element to the gravitational calculations we can do with horizons, black hole, and cosmic. And for the cosmic, it's been particularly confusing. And one goal one might have, not all goals we would have, but one goal is to see if there's a sensible formulation that exhibits a statistical interpretation. Okay, we all know the case of black holes. And the only thing I'm going to key off of that is a different kind of analogy to that than people have been making lately. This goes back more to the earlier part of that subject where, of course, there's famous microstate counts of very particular black holes that had been controlled by starting from some easy regime and deforming, counting the states, showing that they don't change. The count doesn't change, and deforming to where it would become a real black hole. The subject has, of course, moved far beyond that. This was a part of the puzzle. And the reason I'm highlighting that is we're going to take a similar approach of deforming something we know. It's going to be a lot uglier, but it will have some element of this. Okay, so there's lots of works over the years. Most recently, I guess, Juan's paper on the phase, and Anino, Stanislaw, Sun on other aspects of one loop. In the most recent case, bringing in a time-like feature to take into account its effect on making the entropy real. But anyway, there's this classic path integral approach to trying to read off an entropy also for the cosmic horizon. And there's been a suggestion over the years that there could be a finite Hilbert space that captures that. It's not super clear what the interpretation of this calculation is a priori, but at least by some kind of analogy, we can ask this question. So I already sort of said this in words, but in general, when we try to interpret these types of calculations, we really want to understand what these quantities are supposed to mean. With regard to the energy, I just am reiterating here that having a time-like boundary that we take seriously immediately makes sense of energy being a thing that is not constrained to zero. So this is like with gauge theory, where you can have a net charge in a system with a boundary, in contrast to how Gauss's law forces you to have zero net charge in a closed space. And similarly for gravity, there's the Hamiltonian constraint in a closed space that would constrain your overall notion of energy to zero, but with a time-like boundary, there is a surviving notion of energy. In all these cases, it's basically some radial derivative of a bulk field. And for gravity, the correct definition of that is the Brown-York, so-called Brown-York or quasi-local stress energy tensor, which is the thing you would be led to think about. Once you have a Dirichlet boundary condition, you can then compute the stress energy tensor of Brown and York by varying with respect to that boundary metric, again, in a regime where that's a sensible thing to do. And working for classical gravity on shell in the bulk, taking that variation, you get a particular tensor from that, which depends in this way on the extrinsic curvature tensor K. It has nice properties if you have a time-independent set of boundary conditions for the whole system. Then this tensor is conserved, for example. Okay, so energy makes sense, as I've now already been a broken record about. if you want to think about other quantities like temperature, then in this Lorentzian setting, you can maybe think about that through an Unruh detector that is sort of riding along the boundary. There's a volume of the boundary that is fixed by the boundary condition. It's part of the intrinsic geometry there. And in this setting, we can make sense of these various thermodynamic quantities in this way. One of the beautiful things that came out when people looked at that again in relatively recent years in these papers is that there had been a confusion about the first law of thermodynamics. It had sort of looked like if you didn't have this Brown-York energy, it looked like you had a first law, which was like dE equals minus TdS, so a weird minus sign. But if you take the notion of energy to be this Brown-York energy, well, then you get a positive sign there. So that goes along with everything being more like the familiar case we're used to in ADS-CFT holography. So there's that. Okay, and also this recent work on the phase goes in that direction. And when people first tried to understand what the stress center is for ADS-CFT, they invoked this Brown-York stress center in this old paper by BJ and Pear. Okay, we all know ADS-CFT. We all know that the boundary is in some reasonable way associated with short scales or high energies and vice versa. And as I said, our approach will be to deform this. Okay, so how do we deform the boundary conditions? Well, it's known that double trace deformations or more general multi-trace deformations have the effect. Oh, Daniel, do you have a question?
Well, I'm not sure if you want to do questions now or later.
No, I do. I should have been stopping to let that happen. Sorry, I'm in my own world here. Please.
Yeah, I mean, so I've asked you versions of this before, but so you say that having time-like boundaries is generic. But of course, that assumes that time-like boundaries make sense in quantum gravity. And I guess we certainly know some cases where they make sense. I mean, obviously the ADS boundary, but also things like the edge of a bubble of nothing or end of the world brane in string theory or something like that. Usually they have some tension, as far as I know.
Well, you say usually. I don't think we know.
I mean, the ones we know. Usually, yeah. Usually is like your generically. So yeah.
Well, sorry, I think your usually is what is generic in the existing literature, not
Yeah,
what
I mean what I know about.
Well, okay. Okay.
Yeah.
All right. So I'm being a little bit what's the word I'm looking for? Cowardly in stating this as an assumption. I think there's a lot of evidence for it. I also think there's a line of argument we could make where we're gonna you could take these double trace deformations potentially as a definition of it. But for now, I'm saying that indeed, given that they exist, say up to and including low energy string theory and M theory, then all these things follow.
Well, for example,
Take it as an assumption, but
Yeah.
But there's a lot of evidence for it, not just the bottom up thing here, but also I mean, there are some other papers. So there are papers by Almudena et al. That have been looking at this in perturbative string theory. There's a version I had where it was like a glorified Liouville wall. And I think there could be a sense in which we define it by this kind of double trace deformation, which again, I'm not going to claim here. I'm stating this as an assumption for I think the reason you're getting at. But one thing I'll argue back against you about is taking what we quote unquote know as the way things are, because there's so many situations where that's a mistake.
I wasn't trying to say can't happen. I was just asking,
Yeah.
If it's an object, if it's a dynamical object, then it can run in loops. It can be produced in pairs.
Okay, good. But we already know enough about this to say what I'm talking about is different from those things you have in mind. Yeah, so there's no tension. This is what I was saying here. From the bottom up, these statements that I'm making are very clear. It's not you're asking a top-down question, which is fine, but I'm saying it's very clear that this kind of topology in GR and plus matter is not does not carry attention. So you can see it from this
Yeah.
type of solution. So I think it's a good thing to continue to diagnose. I think there might be a line of argument where we can, we don't want to be circular, obviously, but I think there could be a line of argument where we use these double trace deformations, which are being implemented at the level of making sure the boundary conditions that we need are local at the boundary. And there we could potentially get a existence argument from that. So that would kind of bypass the workup from perturbative string theory thing, because these deformations are set up so that they fit with the dynamics of a finite boundary. So I think one can push on your question in two ways. One is, kind of first order business is this GR thing, which is settling down, and then say perturbative string theory, or maybe some BFSS thing with a wall or whatever. And then but maybe also we can make a non-circular argument based on these kinds of double trace deformations, which I was about to discuss. So yeah, thanks a lot for the question. Again, the cowardly answer is I'll just say it as an assumption, but I think there's more to it.
Okay, thanks.
Yeah. Yeah, and I think maybe another, just to add one more thing, if you're skeptical, then I think maybe push for a no-go, but I think you'll have trouble with it. My guess is that would be difficult. Anyway, so we do understand at the level, at least of semi-classics, how to deform the boundary conditions in this way. We do know that much. So and it's very, very concrete. And the way we will do it, we will get this kind of feature that we need, which is a finite state count. As I said, it's going to be kind of elaborate, but I'm going to hope to have time to go through it. So how does this derivation of the double trace deformation that's needed come about? Let's do 4D gravity. It will also include matter. It's similar for matter. So take the Einstein equations. Take in this setting with a Dirichlet boundary at some radial position. Consider particularly the equation that I had already mentioned, the radial one, the kind of analog of the constraint. So take that equation, plug into it. So that equation includes some dependence on the extrinsic curvature, and trade that extrinsic curvature for the Brown-York energy tensor. And what that gives when you do that move is you get an equation that's of the form trace T equals stuff. And next, you can use the fact that trace of T generates scale transformations. And we're looking at a deformation that depends on one and only one scale, which we could trade for. There's a dimensionless coupling, which is some coupling lambda divided by the spatial volume of the sphere to the 3/2 power. So we can consider the deformation to be in either the numerator or denominator of that. So I've kind of written it both ways here, but the point is we then obtain an equation for the deformed action, or equivalently the Hamiltonian, in terms of some quadratic combination of stress energy tensor components, which in the four-dimensional case, Hartman et al. Worked out for us, and here it is. All we've done at the moment is put a sub r here to recognize that since we want this to work at finite n, we're going to have to do something about the fact that this operator is irrelevant, and we need to define it somehow. The other thing that I want to highlight is what we call lambda 3 in this dimension, similar to lambda 2 in the lower dimension that we were going on about for some years. And in this calculation, lambda 4, the four-dimensional CC is proportional to this parameter eta that I've written, and that enters into this term, this lambda term. So yeah, just same parameter as this. And in our elaborate deformation, we're going to start with the analog of pure TT bar called T squared in this dimensionality with this lambda 3 not on. And then after we uplift to the sitter, it'll play a role. We'll turn it on. Okay, so, oops. Okay, did I go up or down? Okay, so I said there are going to be two main components. I'm going to start with the solvable one, which is the fun part. So here's how that works. You take this derived double trace deformation that we need to all be in place to change the boundary conditions the way we want. We're then going to define the solvable piece, which is this T squared solvable plus the constant lambda 3 within this differential equation. For that part alone, we'll define it in the following way by taking this operator that Hartman et al. Constructed, but substitute in this form of the stress energy tensor components that are appearing there. So now this will not capture everything, but it will capture the most entropic configurations, which after all take this kind of equilibrium form. So that's in a nutshell why it's an interesting thing to do, even though it won't capture everything we need. We're going to need to do heavy fine tuning for the rest, as I already said. Okay, so what happens if we just do this? Well, for those who know about the TT bar deformation, where you can solve for the deformed energy levels, it's exactly like that. So this part by itself in this equation gives you a set of energy levels that you can track. You can solve for how they behave as you change that dimensionful deformation parameter y that I mentioned. And here are the formulas. They have the same kind of structure that you might be used to in lower dimensions. If you haven't seen that, just at this point, you can see that there's a simple differential equation that applies once we make this substitution. And I'm telling you here that this is the solution of that differential equation. With certain integration constants in that equation fixed to match to the kind of deformation that we are interested in here. So, it's a differential equation. There were integration constants in there. I fixed them so that, first of all, we start from a ADS-CFT system, and then the way it works at the solvable level, underlined here in green, is that you just keep going with this deformation. At some point, which we call y sub u, you've reached a point where at the top of the spectrum, okay, let me back up. So the square root, I should have said, is important because once we set the integration constants such that, as I was saying, we start with ADS-CFT, you can immediately see that when you do this deformation, you have a phenomenon where these energy levels that you can track, that you can solve for, there's only a finite real spectrum. So if you take this curly E0 for any energy level n, and you take it, which is our notation for the seed theory's energy spectrum, and you take those energy levels too high, well, this dressed energy, so to speak, becomes complex, and that gives you a natural place to cut off the spectrum. So the point is not that we're just arbitrarily cutting off the spectrum. We're doing the double trace deformation that you're supposed to do to make the boundary smaller. We're doing that, not just some arbitrary thing. And having done that, we are led to a finite real spectrum. And this goes back to earlier papers that are important in the holographic discussion of TT bar. So there's that aspect happening. And then this elaborate thing, just at the solvable level, involves taking that deformation up to some point at which we have a spectrum at which, at the top, as I just explained, the square root here will go to 0. It's on the verge of going imaginary. And at that point, we take our deformation and we start to include this lambda 3 after which we make the boundary smaller again. So we start with ADS-CFT, we have an infinite boundary, we make it smaller and smaller and smaller until some point. And now we, at that point defined by this y sub u, we then change the value of this parameter eta, or equivalently turn lambda 3 on in this formula. And then we, having turned it on, we then keep making the boundary smaller. The point of that is hidden in this formula, where you see that the evolution of the system changing the size of the boundary will build up the radial geometry of de Sitter if we have this lambda 3 on, whereas it will be ADS if we don't. Okay, so having said that, let me take Stefano. You have a question, I think.
Yeah, I just wanted to ask, I might have missed this, but is there a natural place where you turn on lambda 3, or is that an arbitrary choice?
Yeah, so in a lot of the earlier papers, we specifically did it at the Hawking page transition level. There's nothing that really forced us to that. It was just a simple choice. That's why I've put a little, I've put a little sub u here to say it can be, we have a de Sitter landscape with many choices of CC, and we have various ADS CFT systems, and you can interpolate from one to the other. And so there is a parameter for that. Yeah, it's a great question. The integrate, whichever choice you want to make in that regard, you can express in this way with these integration constants, where I should say this E0 black hole is related to the fact that in the original ADS CFT system, these most entropic states are black holes, and we go to the horizon of, we go to some place where at the level corresponding to some black hole, we're hitting the square root going to 0, and then we turn on lambda 3, and then we reduce the boundary size. And yeah, we can do that, to your question again, in a way that matches to different values of the de Sitter cosmological constant.
So whenever you turn it on, whatever choice you make, you always land on a well-defined theory, which is dual to de Sitter.
Well, I don't think we have a way of doing that going below Hawking page. I'm not sure, but at least at or above it, we do. Maybe there's even more optionality. Yeah, okay. So what is going, so I just was saying this thing about doing it a certain amount and then adding lambda 3. And what is going on at the top of the spectrum is you have the boundary hitting the horizon of some black hole. If you think about a bounded black hole horizon, very close, you really can't tell, at least in the external dimensions, what is going on with, whether that's actually an ADS black hole or a cosmic horizon. They look the same. In the extra dimensions, they look different. And so when we bring in matter, we drag the system from the ADS value of the scalar fields in the landscape to the de Sitter value. At the level of this solvable system, that is captured by the change of sign of this parameter eta. Okay, so that's how it works, what's going on at the top of the spectrum. So far, we haven't captured reliably, anything else. The other states are doing what they're doing, but they don't look local in the bulk yet. But that's the solvable part that I was saying. So let me move on to the rest of it. The rest of it is, I don't want to. I want to emphasize the rest of it is going to be a huge fine tune, but our point is that we can do it. So the most entropic states are, black holes before we, already in ADS CFT. And then in de Sitter, the most entropic state is the quote unquote empty de Sitter, but top of our spectrum. Once we start exciting matter fields, including gravitons and 4D and so on, then those are less entropic, but the theory needs to reproduce their dynamics as well. Okay, so I don't really think it's this bad, but our sort of immediate way to show that that is possible is simply to point out that although our system is finite, it has an enormous number of states, and it has plenty of capacity to fine tune to define the double trace operators that we need to keep adding, working at finite ends. So now what I'm doing is to use this t-squared solvable only for a little bit, for a cutoff that's above any scale we know anything about. Remember in ADS-CFT that it takes an infinite energy to get to the boundary. So our cutoff is obtained by this tiny little increment of this solvable t-squared deformation. After that, we're going to start to include not just the solvable thing, but also a fine-tuning procedure. We think of it as a kind of algorithm because we tell you what to do to go to the next step of this deformation. And that's, long story short, we're just going to fine tune it. So we can define the double trace operators that we need, even though they are irrelevant. We have a finite system. We can match them to their dynamics in the bulk easily we can match it to the resolution of the low energy theory calculations. So, even though the semi-classical theory looks like it has a continuum of states, that's completely unjustified. In fact, it has resolution only down to something bigger than the Planck length. And so, we can, if we had to, just fine tune this thing at every step to match the local dynamics, which is less entropic than the main point, which is the state count of the top of the spectrum, then we could do that fine tuning at every step. Okay, so, oh, Dan, hi, sorry, go ahead.
Yeah, I had another question just to make sure I understand what you're proposing here. So the idea, I think, is that we have an ADS vacuum, and then somewhere nearby we have a de Sitter vacuum. And
let's talk. I'm going to talk about the uplift shortly. So,
well, yeah, I guess I was wondering when you solve the bulk equations of motion that you have to know through the barrier between the ADS and de Sitter, that all has to be semi-classical and.
So good. So this is a great question, and we
can postpone it if you want to postpone it.
I'm definitely going to address it. It's a good question, and I'm going to talk about it. So okay. Let's reconvene this discussion after I get there, if you don't mind. It's coming up. Yeah. Okay. So part of the answer to your question is it's going to depend on, it's going to be related to this thing where, so my view of this whole thing is we don't need holography to redo calculations of effective field theory. It's nice when you can do it independently, both sides, but it's not really required. And so let me now come to some of these things. Daniel was just asking about the uplift, and there's another aspect of this, which is why does this tuning part of it, why does it not ruin the nice things that I was trying to share about the solvable part of it? Well, the basic answer to the latter will be just this point that we have enough capacity to do this tuning, and we don't need a different state count for that. Okay, so there's lots of ways people have looked at de Sitter. The most recent is, and in my view, a kind of sweet spot for making it simpler is these compactifications that are based on hyperbolic internal dimensions, starting from, say, M theory or 11D supergravity, where there's no extra dilaton. And these have a lot of simplifications that go along with that. I don't have time to explain all of it, but just for what we'll need, there's some uplift, meaning some ingredients you can consider starting from an ADS-CFT system, which is the M2 brane system, and you can change the internal geometry there, which was an S7, and in some sense do some topology change to raise it up to a negatively curved internal space. And there's a long story about handling the inhomogeneities in the manifold. There's a long paper about that, another one that we're writing up. There's a nice talk about this at Strings by Bruno, and I don't have time to explain this much at all. but just sort of related to Dan's point, the picture, including the assumption I made, which is that we can do this topology change through some trajectory in the configuration space of M theory. The picture would be something like this. And the thing that we do to do this uplift, the thing that at the level of the solvable theory is captured by changing the sign of the parameter eta, in this full scheme, we need to do that with the matter fields, this phi sub u that takes us from one to the other. There's some boundary value of that field that we drag from its ADS value to its DS value, corresponds to some coupling in the boundary theory. That is to say, it multiplies various operators, so not just the corresponding operator, I'll just call it O sub u, but also there are many things going on when you uplift from a sphere to some more complicated hyperbolic space. So I've just schematically packaged that as some phi perps, some different other fields whose masses will change as we change phi u. And so we can capture that well within the degree of validity of the low energy theory by including this uplift procedure subroutine in the algorithm, if you wish. Okay, so Daniel was asking not just about this picture, I think, but also about what sort of what is under control, I think, or maybe you can rephrase your question. But okay, here I'm bringing in again that such deformations are familiar. Topology changing transitions, while they haven't been studied here, are familiar in many places in the string landscape, including the closest relative I know, which is a winding string mediated. So condensation of winding strings can change the genus of a Riemann surface in the target space. So we have in mind something like that happening here. Nobody's worked it out. I'm stating it as assumption 2. But notice that things like these wrapped objects are very low energy compared to the energy scale of the most entropic top band of energies. So this is within our expansive definition of the low energy theory. So, okay, so this is admittedly a little bit of a short summary of how we treat these both the matter fields and the rest of the t-squared operator that includes 4D gravitons and so on in the deformation. But I think this is what I was thinking would be related to what I think Daniel was asking, which is one thing you might notice is that, okay, this uplift is happening. We're at the top of the spectrum. We have this boundary, which is skirting our horizon. That is, a very high temperature situation. If we think, say, about an Unruh detector that is riding along the boundary, or if you were to go Euclidean, you would see that, the beta is going to 0. And so, that situation is actually not governed by low energy effective field theory. In fact, in a certain sense, I've thought that's a kind of a feature rather than a bug, because it means that whatever's going on internally, you can't help but kind of mix with all these different compactifications. You're at such high temperature in this sense that it wouldn't really make sense to fix that. But in this kind of I think the thing that's making this work is that we recognize what we need holography for and what we don't, and what we know and what we don't. And the fact that we don't have that much to match here is in some sense a feature rather than a bug. That is to say, there's nothing about that system that the low energy theory tells us. Our Hamiltonian can simply define what we mean by this. And so what we do is we force it to agree with the spectrum of fields that includes those that will be there in the uplift, which will become under control on the gravity side when we pull the boundary down toward the pole, so reduce its size. And so we can easily keep those operators in the game in this tuning algorithm without needing to match anything else that's going on at this point. We can just treat it as if we can just make sure our tuning algorithm keeps track of these operators that are going to be important when we need to match them as we pull the boundary back toward the pole of de Sitter. Okay, so that's essentially our answer to this kind of question that I think maybe Dan was asking. And again, none of this affects the fact that the state count is good for the Gibbons-Hawking and the radial geometry is good at the level of the solvable theory. Even though it's an enormous, although subdominant entropic set of states we're talking about here, we can tune them all because of the fact that the low energy theory, the whole point of quantum gravity is we need a completion of the low energy theory. It doesn't tell us everything. Far from it. Okay. I've said this in a way that was maximally ugly. I don't think it's really true that one would have to retune in this approach everything from scratch at each step of the separation. I don't think so. I think at a given step you have locality. The thing you need to add is going to be able to benefit from the fact that the Hamiltonian at this point has those good properties. We don't expect that you really have to retune from scratch at every point. And maybe sort of more concretely along those lines, when we in the 3D matter paper where we treated matter in the bulk in this tuning way, we did some computations, quite a bit of computing of the energy spectrum and dynamics of matter fields bouncing around in the finite cavity. And one thing to note about that is that the Brown-York stress tensor, which has the square root part, got modified by matter in a way that was outside the square root in this perturbative gravity plus matter regime. So in that sense, there's a structure there that's more appealing than just I'm going to tune everything from now on. Instead, the way the matter appeared was multiplying the square root piece. Okay, so for fun,
Sorry, Eva, can I just push a little bit more? So in
Yeah.
this regime where everything is really hot, where the surface like comes in near the horizon, yeah. Do you need to know how to solve the bulk equations of motion and that? Do you need to, well, just need to know what they are or something when you do this evolution where you modify TT bar using the bulk dynamics? Don't you have to know, why don't you have to know the bulk dynamics here in this hot region? Or maybe you do, I don't know.
Well, I'm not saying that you have to. I'm saying there's nothing that is known that we have to match, so we don't have to know that. What we are doing is tuning so first thing we're doing is noticing we're going to uplift so that parameter eta in this, which really fits into the solvable part of the theory, is evolving to the de Sitter value. Okay, so that's one thing that's happening that we of course need and that we still have. The other thing we need is that the matter fields and stuff that are going to become, things we need to match are going to become under control as we pull the boundary back. We need those things in the game. So we need them to, have the masses that they have and after the uplift and all that stuff has changed and there's, symmetry breaking and so on. So like I said, it's very ugly and elaborate, but all that stuff can be incorporated into the tuning without, as you say, having anything we actually have to match right at the boundary, right at the point where the boundary is against the horizon.
But you want to make sure you end up where you want to end up, right?
Exactly. You make sure that you end up where you want to end up. You can do that in a way where you keep track of the Hamiltonian that's going to do that for you. And as far as we understand, this theory can fill in the unknowns about quantum gravity that go beyond that. So the idea is this seems to give a prescription for matching what we need to match at low energies, filling in what quantum gravity is supposed to fill in. Within particular, the point of quantum gravity, as far as I'm concerned, being to address this question of what is the meaning of the Gibbons-Hawking entropy. This is not a nice way of, recalculating or seeing the emergent spacetime, aside from the radial part, through sort of independent calculations. It's not interesting for that. It's just that this can be those things can be incorporated.
Well, I feel a little nervous, and maybe I'm just not understanding, but because you say you're tuning a lot of things, and what if one of the things you're tuning is the de Sitter entropy, right? How do you know you're not just
No, very good. But good. So let's pause on that. So the argument for that is, I put it various places, but look, if we had a complete gravity side that we needed to match, well, the gravity side would be solved. It would already know about, and I mean in detail, not some nice Euclidean gravity computations, but I mean in detail. It would know so much that we wouldn't need this kind of dual formulation at all. As it is, the argument is the low energy theory that we know we need to match has pretty crude resolution, right? So, you can say, okay, it looks like there's a continuous spectrum of, say, black hole states, but that's not true, right? You know that you can't resolve below, the Planck length in the bulk in EFT and GR, and so you need some hierarchy there, and you can see easily that because of that, you can tune to all those things within that resolution using this finite set of states, because this set of states is so enormous, right? It's not so the idea is that it has capacity to do all that tuning. We might not like the tuning, it may be ugly, it's certainly not how we would do like model building or something, but the argument is that we can, and that indeed we don't need some radically different count of states to do that.
But are you fitting the de Sitter entropy, or are you computing the de
No,
Sitter?
the de Sitter entropy, that's why it's interesting to us, is that the de Sitter entropy part of it is captured beautifully by the solvable theory. So let's back up again. If we look at the bands of energy levels that correspond to the most entropic things, the horizons of black holes and the cosmic horizon, that stuff is captured, beautifully by the solvable part of the theory. It's a combination of incorporating the correct double trace deformation to, to speak loosely, bring in the boundary, change the boundary conditions so we have this finite boundary. And that, having done that, having put in the correct double trace deformation, you see that automatically the energy spectrum, the real energy spectrum for a unitary system, that spectrum becomes finite. And its count of states is the one that you would predict from the Gibbons, Hawking, et cetera, calculations. So you're asking, in my view, the right questions, but it's giving me a chance to try to emphasize why we think this is meaningful, is that there's that part of the system that captures that. It's what really we need holography for. We don't really need holography to redo EFT, even though it's nice when people are able to do that. Okay, so that's sort of the argument. There was this lesson, we think of it as an algorithm for fun. Yeah, so and it's a deformation in this we like to think in the spirit of the old ones for black holes. But for de Sitter, we all know it's harder, and so this is where we're led, is this semi-nice, semi-ugly type of deformation, but it's the same idea. Okay, I've said these things many times. I'm over time, so I could just stop here, or I could say some things about future directions that could help with the bigger wish list that we all have for de Sitter, or I could just stop here. So
maybe we can pause a second and see if anyone has questions, and then we can go on with the future directions. Okay, I'd say go ahead.
Okay. Yeah, I hope I was welcoming enough to discussion, because at least I did see Dan's hand come up every so often. Okay, so as well as yours. So another fun thing that's going on with Aingaron and company is another move one can make, which is, after uplifting, rather than shrinking the boundary to go back here, you can make it bigger, and that predicts that you go up here to this sort of Cauchy slice holography kind of setup. And one check that we have of that is if you just do that and go all the way up here, well, you get probably just because of the symmetries in this case, you get a dressed classical action, which is that of a CFT that's not unitary. So that's a fun thing. And there's also some work by the NYU Abu Dhabi group on black holes, treating black holes in a somewhat similar way. So that's in progress, and we predictably need to straighten out some eyes, but that's I hope we can do that. Another thing is, of course, you might this thing about the spectrum that captures just just these patches I talked about, primarily the cosmic horizon patch and its square root minus sign partner, the pole patch. That by itself isn't claimed to and doesn't by itself capture any larger picture of de Sitter. The larger picture of de Sitter would also be infected with decays that really bring you come to the fore sort of in the what would have been the future boundary of de Sitter. By the way, that mess of states that we tune to includes things with domain walls because we have a connection to ADS. That aspect of the landscape is in there. But it's obviously an interesting question, aside from this approach to it, to see if there's some analog of the whatever it's called, the double-sided black hole, where you entangle, in this case, probably also interact two of these systems. We're not making any claim about that at the moment. It's a future direction. One pet peeve I have is the way people seem to come to dramatic conclusions from Ryu Takuyanagi, and that's something I want to understand better. So, but given that I'm over time, I should probably not belabor this here. But this is not yet covered. Maybe could be obtained in this way. We'll see. Okay, so now let me really stop. And thanks a lot for your attention, and sorry for going over.
Thank you very much, Eva. And anyone that has any questions, we have time for those. Mark?
Yeah. Yeah, I just had a general question. So is there a reason why if we have time-like boundaries as a viable object, could I have a time-like boundary kind of on the inside, like a little object with the so instead of
Sorry, I'm going the wrong way, but let me
outside.
go back up to the phenomenology picture and maybe let me know if that's what you're talking about or if it's something else. So, with or without it actually being there in the real universe, right? We could be us here. There's a boundary. Is that what you sort of have in mind? Or?
Yeah, I mean, I guess I was even imagining something like a 1 meter large time-like boundary floating around somewhere. I mean, is that something that I could introduce? Pardon?
If you're asking, can we exclude that just on general grounds or by some observation? No, that's sort of.
I mean, I'm asking just a theoretical question. Like, could I say I want to do ADS CFT, and so I have a holographic description of that. But is there a step where I could now say, okay, I want to add like this little time-like boundary in the middle? I don't know. Maybe you could call it a little observer, or I mean, is there something where I now add another CFT with a deformation like you're suggesting, and then now I've got a new physical system which is like my old one, but I've now added this extra boundary in there that maybe is moving around.
Yeah, thanks. I like your question. Now that you're saying it, I recall you've asked this before, and we have yet to answer.
Maybe
But
I guess
think
we talked about something like
I
that.
think what you're saying is, I've been sort of harping on that we certainly don't know that the positive cosmological constant comes without a time-like boundary. You're saying, what about extra time-like boundaries within ADS, essentially?
Yeah, just
Yeah.
like if that's a new thing that we have to work with.
Yeah, I think that would be interesting. I mean, for what it's worth, the exercise that I did at one point was to see if there's even at the sort of leading level some analog of a Liouville wall, which could cut things off within ADS, like one of those versions of ADS where you have some worldsheet handle like NS. Yeah, I don't think very much has been. Yeah, I think it's an interesting question. I haven't spent enough time thinking about that, what the interpretation would be, and whether or not one could get that from a deformation like this. It is, of course, it does look like it would be something infrared rather than like if you wanted to think about such a thing in the middle of ADS or something. It sounds like it would be naively at least, like it would be more like something you did to the infrared rather than something you did to the UV. So,
Right. Okay, thanks.
Yeah, thanks.
Any other questions? Now let's thank Eva again for the great talk.
Thanks, Eva.